So for this first question, just making sure I'm recording. So for this first question, we are finding the horizontal asymptote for the function. And recall that a line y equals to L is a horizontal asymptote if the limit of the function as x goes to positive and negative infinity is equal to L, right? So what that means is that graphically we have a line at L over here, and this is saying that the function might be going like this, right? And the limit as x goes to like positive infinity, but this function will stay below the line and it will approach but never touch the line. So that's the limit, and that's equal to L. So so something to be mindful of is that uh, x goes to positive and negative infinity, and you need to check for both cases because sometimes um, I might have two asymptotes, right? So for example, this line could be L, and the function might behave something like this, right? So you'll have two horizontal asymptotes, and that's why you need to check both the positive and the negative side. So now let's take a look back at our question. Um, well, we have the limit as x goes to plus or minus infinity of 6x plus 1 divided by the square roots of 4x squared plus 5. So what I'm going to try to do is that just because if you plug it in directly, right? So you have like you will have infinity plus 5 and then infinity plus 1, so that's not going to take us anywhere. So the second thing I'm thinking about is just take the limit as x goes to plus or minus infinity, but this time I'm going to try to factor out this negative x squared. So I have 6x plus 1 divided by uh, the square root of x squared times 4 plus 5 over x squared. And you can see that when I multiply this x back into the 4 and back into 5 over x squared, I will still have 4x plus 5. Um, but now, what I'm going to do with this is that I'm going to uh, try to pull this x squared out. So here I'm going to use this uh, this fact that when you take the square of a square root of a square, this will equal to the absolute value of x and not equal to just x, right? Because if you well, that's how this thing is. And remember that the absolute value of x is defined in terms of two cases. So it's equal to x when x is positive, and it's equal to negative x when x is negative. So if you just use this positive x, you're looking at only this top case and you're ignoring this whole other answer. And that's going to create some problems if you do ignore it. So let's proceed. So with case one, you let x go to positive infinity, right? So here we have let x go to positive and negative infinity. So we're going to examine just the positive case for now. When x goes to positive infinity, we take the first branch, right? So this means that the absolute value of x will be simplified to just x. And now the limit as x goes to positive infinity of 6x plus 1 divided by, um, so before we get to the math here, I can simplify here one more step, right? And that's equal to the limit as x goes to plus or minus infinity of 6x plus 1 divided by the absolute value of x times the square root of 4 plus 5 over x squared, right? So that's gonna get us like this. And now we can simplify from here. The absolute value of x is just gonna simplify to x. So we have x times the square root of 4 plus 5 over x squared. And as x goes to infinity, once again, if you directly plug it in, you have infinity times something at the denominator. That's not going to work. But what we can do instead is we can do this. We can divide every single term by the um, highest power. So in this case, you have x divided by x, so that's gonna be gone, and then 4 plus 5 over x squared. So once again, I'm just dividing every single term, which is these three, by an x. And so this will give us the limit as x goes to infinity of 6 plus 1 over x divided by the square root of 4 plus 5 over x squared. And now when you plug infinity, so this is going to be equal to 1 over infinity, which is 0. 5 over infinity squared, that's 0. So you'll end up with 6 over square root of 4, which is 6 over 2, which is equal to 3. Okay, is that okay for everyone? Does anyone have questions? Okay, um, let's go to the second case. So the second case is when x is going to negative infinity. In this case, when x is going to negative infinity, we take this branch, right? So the absolute value of x is equal to negative x. And that in terms of our limits, so if we continue off just from here, we have the limits of x going into negative infinity of 6 plus 1 over x divided by a negative x times the square root of 4 plus 5 over x squared. And uh, well, we're gonna do the, it's uh, yeah, so this should be divided by x, so this x here is gone, just like how it was gone over here. And if you plug in negative infinity, that will go to 0, that will go to 0, so you have 6 over negative root 4. So that's going to give you 6 over root negative 2, which is equal to negative 3. So basically, if you ignore these two, if you just went with just this one, then you will miss this entire case. So that's why you need to do that. So now we can say that therefore the horizontal asymptote at x equals to 3 um, and negative 3. Okay, and here is the whole question. Okay, so any questions? Okay, let's take a look. So we want to show that this equation has at least one solution. So to show that um, this has at least one solution is the same as showing that if we define a function, so let's say f of x is equal to x squared minus sine x minus x cos x minus 17 has at least one root, right? Because like if you just move everything to this side, so we have just this expression, you want to show that this equals to 0 has uh, has a solution. This equals has a solution. That's the same thing as showing that this function has roots, which is when this is equal to 0, right? So this is equivalence, um, and the reason why I'm defining it as a function is because I want to use the following theorem. This theorem is the intermediate value theorem that says that if f is a continuous function, so continuous, you can check that x squared is indeed continuous, sine x, x times cos x, negative 17. So these are basically all continuous functions. So everything here is going to be continuous um, on a closed interval. In our case, um, all these individuals are continuous from negative infinity to infinity, right? So no matter which closed interval, um, like real numbers you substitute into a and b, it's going to be continuous. So yeah, so this holds. Then for any value L between f of a and f of b, so what is f of a and f of b? Well, let's demonstrate this. So let's say that this is the point A and this is the point B. So then corresponding to the y value right over here, this would be my f of A. And similarly, this is B, so around here, that's going to be my f of B. So this is saying that then for any value L between f of A and f of B, so L is something that's between f of A and f of B, right? So it's gonna be like somewhere along this red line. I'll just pick a random point, say that's equal to here, right? So this is equal to um, L, right? So L between F and FB, there exists at least one point C in the interval AB. So this is the interval from A to B, so which means that C is in this interval such that F of that C gives me this L. So if I just trace it back, C would be roughly around this point. Right? So C is between A and B such that F of C, F of C is L. Right? So in other words, this point here is C, comma F of C or L. Okay, so that's what this theorem is saying. Um, so uh, and it makes sense, right? Because its continuity guarantees that for every single point in the range, you can find a point in the domain that the function maps that point in the domain to the range. So um, how do we apply it in this case? Well, let's uh, let's try to find a value of x, or let me maybe draw it here. So if my kind of my L is equal to 0, right? So let's say that L is equal to 0 because that's going to be like our roots. Then if I am able to find, let's say if I'm able to find an M such that like this is going to be your f of M, and you can find another number, let's say N, so that this is going to be your f of N. Oh, sorry. So M should be on the x-axis. So if I can find an M, so that this is going to be f of M, right? So this here will be f of M. I can find another number N, so that this number here, which corresponds to something like here, that's going to be f of N. Then you can see that, right? F of M, which is here, that's going to be less than 0. And f of N, that's going to be greater than 0, right? So here, f of M is less than 0 and f of N is greater than 0, just because one is below the x-axis and the other one is above the x-axis. So basically, the function is continuous. You can find one value that it's negative and then positive, which means that your function must have traveled across this line y equals to 0 at some point. So therefore, this thing must have at least one root. Okay, so what I'm going to do now is I'm going to start to test for some numbers to find my M and N. So I'm going to bring this down, and I'm going to see. So 0 is always a good number to try out at first. So if you do f of 0 or h of 0, this is going to be equal to 0 minus um, sine of 0 is what is 1 is 0 minus cos of so 0 times cos of, so that 1 minus 17. So this is equal to negative 17, which is obviously less than 0. So our h here could serve as the value as m, right? What about the other value? So I want to find something that gives me that's greater than 0. So what about if I try I mean, just looking at this function, we know that sine x is bounded by -1 and 1. So this is between -1 to 1. This cos x is between -1 to 1. So it really, the maximum that this can do is 1. So that it really depends on this x. And this 17 is just constant. But because this x squared is growing faster than x, right? If you think about the graph of the square root function versus the linear function, the square function versus the linear function, the square function grows a lot faster than the linear function, right? So if you're increasing by x squared, you're increasing faster than x. So if I pick the idea is that if I pick a number that's big enough, then this first term will basically trump all the other terms. So let's say if I pick a term like 20, right? So my first one will be 20 squared. Um, well, I'm going to use this inequality here because I don't know exactly what sine of 20 is, but it's going to be less than, right? So this is at most. This is going to be, so the most that sine x could be is going to be 1, right? So when you're subtracting 1, that's the worst amount of damage you can think about, like in terms of damage that the sine x can do. And then now this x cosine x, when this is equal to 1, this would be equal to 20. So you would be subtracting 20. And that's kind of the worst that this term can do. And then now you minus 17, right? So this is like 400 minus some small numbers, right? So you can imagine that this is going to be greater than 0 for sure. Okay, so now what we have just done is that we found a value of m and we found a value of n such that f of m is less than 0 and f of n is greater than 0. So now what um, we can conclude is that um, since we can just say by the intermediate value theorem, h of 0 less than 0 less than h of 20 means there exists a c in um, 0 to 20 with h of c equal to 0, i.e. there is a root. Okay, and because there's a root, that's the same thing as saying that this thing has at least one solution. So therefore, there is at least one solution to the equation. Okay. All right. Okay. Any questions for this one? So I will say that this is a very uh okay, seems like some people already done, so let's take it up. What we have is using the definition of the derivative to compute the limits. So to explain what's happening with this definition, so first of all, x is over here on my x-axis. This is a point x, and x plus h is over here. So we basically have this increment of h from here to here. And then correspondingly, f of x is over here, and f of x plus h is over here. So what we're doing with this limit is that we're looking at the distance between here divided by the distance between here, but we want to let h go to 0, which means that we want this to get smaller and smaller and smaller. So we basically want to shrink this closer and closer and closer. We make the until it gets like really close. So then we basically have a rate of change, right? This should remind you of the formula y2 minus y1 over x2 minus x1, but we're just taking this x1 y1 and y y2, x2 really close to each other. So what we have is basically the slope of this tangent line that touches this point. That's the intuitive definition of the limits. And in terms of how to find the derivative, we can compute f prime of 8 as, by the definition, as h goes to 0 of f of x here would be 8. So it would be 8 plus h minus f of x, f of 8 over h. So the limit here would be h going to infinity of f of 8 plus h. So that's going to be the square root of 8 plus h plus 1 minus f of, uh, well, the square root of 8 plus 1 over h. So what you can do here now is that you can, because you see the two square roots, you can multiply by the reciprocal, by the uh, the conjugate, right? So this is 9 plus h plus square root of 9. Okay. So now the top is in the form of a minus b times a plus b, where your a is the square root of 9 plus 1, and your b here is the square root of 9, which means that by the difference of squares formula, you just have 9 plus h um, minus 9 over n um, h times square root of 9. Okay, so if this is not super clear to you where that came from, you can just multiply these two, just term by term, and simplify, and then you will get this. Okay, so what's going to happen next is 9 cancels out, h and h cancels out, so you have the limit as h goes to 0 of 1 over the square root of 9 plus h plus 3, and when h goes to 0, this is just equal to 3, right? So 1 over 3 plus 3, which is 1 over 6. And that's all for this question. Okay, any questions for this one? And once again, this is a question that's